The AI for Good Global Summit, convened by ITU, recognizes the joint responsibility of governments, the private sector, United Nations agencies, academia, and others to ensure AI reaches its full potential while preventing and mitigating harms.
And it's a moment that calls for action. And today I'm calling on each of you to use this summit to help the world to better understand what kinds of regulations, what kinds of guardrails we need to put in place right now. So together, let's make it innovative, let's make it safe, and let's make it responsible for all. Thank you very much.
Welcome to AI for Good, the leading action-oriented, global and inclusive United Nations platform on AI. Organized by ITU, in partnership with 40 UN sister organizations, and co-convened with Switzerland. The goal of AI for Good is to identify practical applications of AI to advance the United Nations Sustainable Development Goals and scale those solutions for global impact. In today's session, we're counting on you to use the live video wall feature to ask questions and post comments to help create an engaging discussion. We encourage you to stay until the end to chat, connect, ask questions, and network with our distinguished panelists and world-class AI experts in the neural network. It is now time to kick off the session and welcome our first speaker. The floor is yours.
Yeah, also a great welcome from my side. My name is Gita Couture-York. I have a chair for Mathematical Foundations of Artificial Intelligence at the Ludwig-Maximilians-Universität in Germany, the LMU, Munich, and I also am a founding spokesperson there of the AI Hub, which is a platform for research, teaching, and transfer. And also currently, since some years, I'm one of the two directors of the Konrad Zuse School of Excellence in Reliable AI, which is set up as a joint project between LMU Munich and TU Munich. And it's now my great pleasure and honor to welcome our speaker, Fang Luong, who is currently a senior staff research scientist at Google DeepMind. And he started his career in actually Singapore, where he received his bachelor's in 2008 with first-class honors. He then stayed for a couple of years as a research scientist there, then moved to the United States, to Stanford University, where he received his PhD in computer science in 2016. And during this time, he already pioneered the field of deep learning for machine translation. Then he moved to Google Brain, which is now Google DeepMind. And also there, he made tremendously important contributions in general to the general area of AI. For instance, he built state-of-the-art models in both in language and also in vision. He initiated and debuted basically the world's best chatbot in 2020, and since 2022, he is the principal investigator of the AlphaGeometry project, which aims to solve Olympiad geometry problems at the IMO level, the International Mathematical Olympiad level. And in general, I should say, I mean, he has served as, for instance, area chairs at various top international conferences in AI, for instance, at Europe's. And also, if you look at his publication list, it's extremely impressive. I mean, for his publications, he already received more than 30,000 citations and also holds 15 patents. So I think we are all really excited to have him here as a speaker, and he will give a talk on AlphaGeometry, an Olympiad-level AI system for geometry. Fang, the floor is yours.
Yeah, thanks a lot, Gita. Thanks. I would like to thank the organizer for inviting me. It's my great honor. I hope that the section will be interesting to you all. So let me start by sharing the screen. Okay, so I'm guessing everyone can listen to me now. Yeah, so hi everyone. My name is Tang Leung. So today I'll talk about AlphaGeometry, an Olympiad-level AI system for geometry. So I'll start first by just saying my journey to AI and math. And so the first few, the first part will be less technical, and then I'll go a bit more technicals, and I'm happy to take questions at the end. So my math journey started with a legend who glorified Vietnam for 40 years ago. So by that, I'm referring to my math teachers during high school. His name is Lê Bá Khánh Trinh. He might not be very well known in the world, but he's a legendary. He's very famous in Vietnam because in 1975, during the IMO in London, United Kingdom, he got to be ranked number one in that IMO, and he also got a special prize for having a very elegant solution to the problem number 3 that year, which is a geometry problems. And let me just, maybe some of you might have seen this problem, but let me just state the problem again. It's very simple. Let's give two circle, C1 and C2. They intersect at the point A. And then now that there are 2 points, M1 and M2, both start at the same point A, and they both move with the same velocity. And the question here is to prove that there exists a point P, or just any point on the plane, such that at any time during the traveling of the 2 point M1 and M2, that point will always have equal distance toward M1 and M2. So the solution from the organizer is actually quite complicated. And then when they saw the solution of my teacher, Lê Bá Khánh Trinh, they was very surprised. It's so elegant, and then they use that as the main solution. I can give you a quick run through the solution. So let B be the other intersection point between C1 and C2, and then now let the opposite point across O1 to be B1, and the opposite point across O2 to be B2. And we can see that B1, M1 gonna be perpendicular to the line M1, M2, and then B2, M2 gonna be perpendicular to the line M1, M2. And because of that, if we take the point P to be the middle point of the line B1 and B2, that point P is the actual point that we need to find out that it actually have equal distance toward M1 and M2. So I was inspired by my teacher during high school. I was doing Math Olympiad during high school full time. I got to the national level. I was ranked number 8, but didn't make it to IMO. So I guess that maybe I was so sad at that time. So my journey turned into the new page. Oh, actually, before I talk about the next journey, I just want to give people a quick run through about the IMO. So it's a most prestigious math competition for high school. 100 plus country participate. And then people will participate for 2 days. Each day they will solve 3 problems for 4.5 hours. And it is well known that problem 1 and problem 4 are the easy ones. 2 and 5 are medium ones, and 3 and 6 are very hard. So the problem I just showed you, problem 3, 1979, is the hard problem. So moving on to my next journey, right after high school, I have been doing AI for nearly 20 years. And thanks for the introduction from Gita. I defended my thesis in 2016 on the topic of neural machine translation. Basically, during that 2 years, we changed translation entirely. And the improvement what we got during that 2 years is actually equal to what people have been achieved during the past 20 years. And then I was fortunate to continue my journey at Google. So this is a fun picture that I often show people. On the July 4th of 2017, this is like a holiday in the US. Somehow I myself with Jeff Dean, which is the Google chief scientist, and also people often refer to him as the god of engineer, as well as Quocle, my close friend, very famous scientist. And we all somehow happened to be in the office during that holiday day. Maybe we was working so hard. So we took a picture. So during 2018 and 2020, I was very excited about chatbot, about building open domain chatbot. So I co-founded the project Mina, and I think we released that research during that time. It can actually tell jokes as well. It's very surprising to many people. And in fact, we compare with a lot of chatbot at the time, like Mitsuku, Cleverbot, DialogGPT, CellEye. We outperform those bots, and we are coming very close to humans. We didn't get to release a bot, and I think you all know what happens afterward. But I think fast forward later, we have a launch a bar, generative AI in 100 days. I think it's probably the fastest launch ever. And I think it was an exciting time. So we make so many progress with ChatGPT, Bard, Gemini. So why math now? Why talking about math at this time? Well, maybe because you can be quite rich. There's a new prize for someone who can build a computer algorithms that can achieve gold medal at the IMO. If you can build that, you can get $10 million. With the fact that that model need to be publicly shared. Well, joke aside, for me, I think math is a testament of like whether AI can do advanced reasoning. So for model like ChatGPT, Bard, Gemini, if you give it like a simple math problem, like I have 4 balls, and then now I buy 2 more basket, each have like 3 balls. How many balls do I have right now? So it's gonna be 4 plus 3 times 2 equal 10. So these are very easy questions for the latest large language model like ChatGPT, Bard, Gemini. However, when we start to give them Olympiad problems, they all fail. And I think because they didn't have the capability of reasoning for many steps, and the capability of seeing the entire big picture, how to connect everything together. And for me, I believe that in order to reach AGI, which is artificial general intelligence, meaning an AI that can be better than human across many tasks, we need to be able to teach math. We need to be able to teach AI to have the advanced reasoning skills. And in fact, I believe, like I just talked about it during the year 2020 until now, many people talk about things like Turing test and chatbot. But I think the next phase would be about math test and AI for math. I think it's gonna be it's very close. I think maybe in 1 or 2 years we're gonna see a lot of breakthroughs, a lot of discovery in terms of using AI for math. And that brings us to this paper that I'm very excited about. This is co-authored with Triu Jin from the NYU. He just joined us at Google DeepMind. Tony Wu, formerly at Google, now it's XAI. Kwok Lee at Google DeepMind. Her as NYU. So the main points of this paper is we can actually solve Olympiad geometry. We can build an AI to solve Olympiad geometry without any human demonstrations. So that's how there was some progress in AI for math, where people teach the AI to learn from how humans solve problems. So they show the AI human written proof. Here we don't have any of the human proof. So what is AlphaGeometry? So it's a neurosymbolic solver where there are 2 parts. There's a neural part and there's a symbolic part. So let me walk you through a simple problem. In this case, let's given a triangle ABC, and then given that AB equal to AC, the question is, can we prove that the angle ABC here is equal to the angle ACB? So when we're given a geometry problems, what we do is we're going to send it to the symbolic engine first. If it can solve, great. But if it can't solve, then we will go to the language model and ask, hey, can you give us some suggestions? Can you suggest some lines and points for us to construct? Because if you remember your secondary high school time, when we solve a geometry problem, oftentimes we need to find out if there's any interesting new lines and points we can add to the problems. That will make things much easier. So this is what we call magic construction. And in this case, the neural network suggests that, okay, let's construct point D, which is the midpoint of the edge BC. And because we have AB equal to AC, we have BD equal to DC, and then the common edge AD here. So we know that the true triangle ABD is equal to ACD. And then from that, we can derive that this angle B also equal to this angle C as well. And if you read the book Thinking Fast and Slow, this kind of neurosymbolic solver is really like system 1 and system 2, where the neural network is actually quite creative and fast. However, if we let it to run through generate long solution, it's gonna start to hallucinate, which is a problem that we observe in language model. On the other side, for the system 2, it's actually quite reliable. One, we have everything. We have the kind of magic construction. We have all the rules given to the system 2. It can figure out everything, the rest of the things, easily. But it can be slow. So then this is a perfect combination. So system 1 and system 2, the neural component and the symbolic engine, they work in tandem to try to solve this geometry problem. So here's a more advanced example at the IMO 2018, problem 1. So I won't go into detail of the problems, but the question here is, can we prove that this line DE is parallel to the line FG? So the hard part here is actually how to construct the midpoint. So here's the kind of rabbit or the magic construction is, we're gonna construct M is the point of the arc AP, the midpoint of the arc AB, and then N is the midpoint of the arc AC. The moment we have those constructions, everything becomes simpler. The symbolic engine can work through them and solve the problem quite easily. And they can solve by proving that MN is actually perpendicular, is actually parallel to DE, and MN is parallel to GF. That leads to the fact that DE is parallel to GF. So we want to do magic construction, but the question is, how do we teach AlphaGeometry to do magic construction? So I'll give you an overview. So the key question, the key answer here is synthetic data generation at scale. So this is the second idea. The first idea is neural symbolic system. The second idea is synthetic data generation at scale. And in fact, if you remember your high school, secondary school, oftentimes when we want to learn geometry, we take a pen and paper, we try to draw some diagrams, we add some points, lines, we try to really understand, appreciate the picture, try to figure out what are the properties that we can find out from these different diagrams. So this is a kind of inspiration that we use to build the data set, the training data for AlphaGeometry. And here's the more a little bit of a zoom in. So let's say we have 3 steps. So step 1, we sample random diagrams, and from that we are given different facts. Then we look at the rule tables. So these are basic rules that we give to our data generation process. And then it's gonna derive new facts. For example, like there's a cyclic, so EADH is on the same circle, or it's gonna derive that the HA is perpendicular to BC. And then different path will lead to different problem and proof. For example, this one is a simple one where we prove that the angles is equal to 90 degrees. This one where we sort of prove that the 2 angles here are the same. And there could be also more complex one like this one where we prove that all the 3 altitudes intersect at the same point, H. And to zoom in even further, this is how we generate syntactic theorem and proof. So I'll give you an example in a very simple setup. So there are 3 steps. The first step is sampling. We're going to sample mathematical facts. Let's say A equal to B, and B equal to C. And then step 2, we're going to deduce new property, new mathematical facts. So by applying transitivity of equality, we can derive that A is equal to C. And then this is a tree that we obtain. However, to teach a language model to be able to learn, we need to turn that tree into a sequence of a string sequence. So in this case, we have theorems. Let A equal to B, B equal to C, prove that A equal to C. And then the proof is just applying the transitivity of equality on A equal to B and B equal to C. So this is a simple case. If we talk about the geometry case, then what we will have is, first we have the facts, AB equal to AC, DB equal to DC, and DBC is on the same line for this figure on the right here. So once we have the leaf nodes, we then go up the tree and build a tree. So we will have first, we figure out that there's an angle ABD equal to angle DCA. And then from that, we're going to figure out the triangle ABD equal to triangle DCA. And then from that, we're going to have the angle ABD equal to the angle BCA. And that gives us the new the string here, the serialization process. The string, let's say there's a theorem, there's a question proof here, and here's how we're going to solve that problem. So this is one training example in our data set. However, if you look carefully, so there's this blue part here about the D midpoint of BC. So actually, this is like a very uninteresting theorem, because we are given everything. Like we've even given the fact that D is a midpoint of BC. However, if we, so actually this that D is actually necessary for proof, but it's not necessary for theorem. So if we ever move that fact, the D is a midpoint of BC, to the proof side, then this actually become a very interesting theorem, because it's only given the fact AB is equal to AC. It's harder. So it doesn't give the fact D is a midpoint. And we move the fact that actually the kind of insight into the proof. So we can think of this as like, we teach the language model to think before solving. So this is like what you see at the bottom here is a whole string that we're going to pass to the language model. So when it reads the proof problems, and then they see the word proof, it would then, okay, so first I need to think about what are the new insight, what are the kind of magic construction I should suggest first before I go on and proving things. So you might wonder, how do we know that D is a midpoint of BC is a magic construction? So let me go in a little bit deeper on how we can identify that magic construction. So again, we build a tree that you see previously. So the next step we're going to do is we do conclusion traceback, meaning that from the conclusion here, we figure out what are the leaf node that this conclusion depends on. So we have the set DC. And then from that, also from the conclusion, we try to do object traceback, meaning that in that conclusion here, there's a point A, point B, point C. These are the objects, also the angle objects, ABC, and the angle object BCA. And when we trace what are the leaf nodes that lead to these objects, this is the only leaf node that our algorithm found, which is D0, DO. So then we can actually do the dependency difference. So we realize, oh, actually, these two leaf nodes, these are needed for the proof, the tree itself, but actually not needed to construct the conclusion object. And this is how we figure out. So these being the midpoint of BC is actually the magic construction. So let's take a step back. If we think about this process, about building a tree, conclusion traceback to get DC, object traceback to get the set DO, and then the dependency difference, DC minus DO. It's actually kind of general. And it doesn't depend on the geometry, so it might be applicable to other domains of mathematics. However, we don't want to give a false impression here. Is actually this our strategy applied right away to new domains of mathematics? I think this is a kind of inspiration, kind of the idea that might be applicable. Because just for geometry, it's already there's a amount like non-trivial amount of work needed to make this work. For example, even before this step, first we need to have the kind of domain-specific language, in this case, geometry. And then we need to have a set of rules for the symbolic engines to explore, to deduce things. So in our case, we have a set of the very basic rules. So once we have step 0, well, then for building the tree, we need a symbolic engines, in this case, DDAR, that we built, that we extended from the previous DD system. And for conclusion traceback, we have to do minimum spanning tree, mix integer linear programming, and then that's so on and so forth. So again, I think this is an interesting idea that I think is actually quite interesting, the way that we can come up with the kind of insights to this language model to think before solving things. And I hope that this kind of inspiration kind of idea can be applicable to other domains. So once we have all of these recipes, so let's talk about the final data. So what we did was we scaled this up on 100,000 CPU workers. We run for 3 days. So we explore like the 1 billion random diagram, the kind of diagram that you saw earlier. So after running for 3 days, we obtained, and then doing some processing, like the deductions, we got about 100 million theorem and proof. So I would say this process is very, very like, it's very challenging, actually. We went through many hurdles. So there's like many subtle bugs and how to get things right, how to get data at scale. I remember we have more than 10 plus versions of the data. So the final version that we got was like V11B. You know, when we got like some of the early versions, like in July 2022, where we got to, once we got the data right, July 2022, we got the first important geometry problem solved. And then by October, after we fixed the data, improved the data further, we got like the first IMO problems solved. And then by December 2022, we were able to get most of the IMO geometry problems solved. So here's a statistics about the synthetic data that we have, the 100 million examples. So what you will see on the x-axis is actually how long is the proof, how many proof steps are in the proof. And we can see that like when the proof step, the proof length is 1, we see very simple things like these two angles are 90 degrees. Or when the proof step is longer, like 20, we discover some familiar well-known theorem. In this case, people are probably familiar with this Euler circle or 9-point circle, very interesting circle in geometry. And then we even look further into our data. There's even example where the proof length can be more than 200 proof steps. For example, these diagrams here, I don't know what it's doing, but it's basically there's a lot of points here, lots of circles here. At the end of the day, the question is to prove that this angle is equal to the other angle. So we also show some of the problem here to some of the experts at the Math Olympiads, and they actually told us that some of the problem here can be at the national level as well. And in total, among the 100 million examples of theorem and proof, there's about 9% of them have the auxiliary construction or the magical construction that we talked about before. And let me talk a little bit about the model as well. By the way, it's actually not a large language model. So it's only 151 million parameters. So I think it's tiny by today's standard. When I built my Mina chatbot in 2020, it's 2.6 billion. Is that already the largest one? During that time, GPT-2 was only 1.3 billion. But fast forward now, I think like we talk about 175 billion parameters for GPT-3, and then people speculate that GPT-4 can be 1 trillion parameters. And we're using the familiar architecture transformer, so 12 layers, A hat, 1K embedding dimensions, 4K hidden dimensions. The vocabulary here is actually quite small. It only has 757 tokens, and the context length is about thousands. But most of our data, 90% of our data, is less than 200. And we were training on TPU V3, Google TPU V3 4x4. So we first pre-training the data, the whole data, over 10 million steps, the whole 100 million examples. And then we fine-tune on the auxiliary, on only those data set that have data points that have the auxiliary construction or the magic construction for 1 million steps. So let me give you just a taste of what the symbolic engine looks like. So we build DDAR, which have two parts, the deductive database to derive the different properties, Euclidean properties in geometry. So, and then there's an algebraic part as well. So let's look at the first part on the left. Let's look at the first rule as well. So this is some mysterious language, but let me decipher them for you. So if we look at the first rule, so it say that perpendicular, so there's an edge AB perpendicular to the edge CD. And then the next part gonna say that perpendicular CD and EF, meaning that there's a edge EF perpendicular to CD. And then we know that the point A, B, E are not on the same line. So that means we can conclude that AB is parallel to EF as well. And you can also see other properties like if we take the midpoint E of the edge AB and the midpoint F of the edge AC, then we can get the fact that the line across the midpoints, EF, is parallel to the edge BC. This is rule 7. And also a novelty in our work is that we extend the deductive database into algebraic reasoning, where we do like Gaussian elimination. So we can do manipulation on the angles, where we can derive that, let's say this angle here is 90 degrees, or we can also compare ratios across different edges. So putting everything back together, so here's the whole diagram about how AlphaGeometry works in action. So when we're given a problem in natural language, so we have to first manually translate into AlphaGeometry language, which is this thing here that you see. So this is actually a limitation of AlphaGeometry. And because of this translation, and we have to do manual, and also we can only translate about 70% of the IMO problems. But there's a nice thing about this language here, that it can be converted back into natural language. And then once we have solved with AlphaGeometry, we can obtain a solution in natural language. And then we can send that to expert as well, for which we did send to expert like Evan Chen, the lead of the US Olympiad team as well. And for the results, here we look at a set of 30 problems from the year 2000 until 2022. There's about 40 problems in total. But as I mentioned to you, the language of AlphaGeometry can only describe 70% of them. So among these 30 problems, AlphaGeometry can solve 25 problems. And if we look at the gold medalist, they on average can solve about 25.9 problems. And then compared to the previous state-of-the-art, the Wu method, it can only solve 10 problems. So this is a big win here for AlphaGeometry. And also it's actually approaching the gold medalist as well. So in the year 2000 and 2015, we managed to solve both problems. So in the IMO, there could be one problem or one geometry problem or two geometry problems. So for the year 2000, 2015, there are 2 problems. And then we solved both of them. So That means we can think of AlphaGeometry as winning, like have won the bronze medal at the IMO 2000 and 2015. So let me give you a rough idea about how the solution of AlphaGeometry looks like. So for the year 2015, problem 3, this is a very hard problem. And what AlphaGeometry can come up with was 109 steps. It's very long, 109 steps, but it's correct. What it did was it construct a few midpoints. So it construct D being the midpoint of BH here. And then a few steps later, it's a construct the midpoint G of HC. And a few more steps, it construct the midpoint E of the edge MK here. And then we also notice things like, it can see this, like the all circle here, M, O2, G, and D. So the step 26. So there are these properties here, but of course to AlphaGeometry, it didn't know that this is Euler circle. It only proved it just like derive all the formulas or the deductions until it get the final goal. And I got a chance to show my teacher. Oh, actually, before that, not just my teacher, but also like even John. So when he looked at this exam, the output is very impressive to him. So it's both verifiable and clean. And then also you basic classical geometry rules such as angle, similar triangle, just like students do. And I just hint to you that last year, 2000 December, I got a chance to visit my high school. I showed the solution of AlphaGeometry to Dr. Trinley, and also there's Dr. Jung Chung here. Both of them are IMO medalists as well. And then what Dr. Trinley was telling me was that the solutions are really remarkable. He actually quite surprised that with such a difficult problem, it can actually prove in using just like synthetic geometry, meaning that it's not using algebraic. Some people can use using like complex numbers, like complex tool to solve it. But these are just like very elementary rules. Anyone can understand. But however, it's not very satisfying to him because whenever he solves a problems, he trying to connect everything. He want to see the big picture. He want to see the soul in the solution, and he didn't see the soul in a AlphaGeometry solution. And he gave me an answer. It fit only a single page, and it's using inversive geometry, which is something quite popular for like IMO students. And it's actually we can derive the solution in less than 20 steps. So this tells us that it could we can in the future optimize for like beautifulness, for for elegance in the solutions. So with that, I just want to summarize. So in AlphaGeometry, there are two key ideas here. One is we do synthetic data generation at scale. We got 100 million examples. And then we basically, with that data, we teach the machine, teach the AI to do some thinking, to think about what are the important steps, what are the important insights to solve the problem, which are the magic construction. And then we have this neuro-symbolic setup for deep reasoning, where the two components, the neural component and the symbolic component, work in tandem to solve the problem. And I think what people would be wondering, what next, right? So I think obviously we're thinking about AlphaGeometry 2, where we're going to extend the language and the formulation so that we can cover hopefully 100% of IMO problems. And we also hope that this will get the inspiration, not just us, and also many others, so we can extend to other domains. We can make further achievements in math. I think IMO is actually a very good goal, but I hope that in the even further future, hopefully AI can go on, discover new knowledge, discover solve new conjecture, so the Millennium Prize. I think that would be a fantastic future. So with that, thank you for your attention.
Thank you so very much for a really amazing talk. I mean, I was fascinated by the results because, I mean, I'm a mathematician myself, so it's very interesting to see, I mean, how far you can already go with AI. So now, I mean, the question session is open. So maybe I start with some. So I found it quite fascinating in the end. I mean, you said that your former, I think, teacher found a much shorter solution. I mean, to which extent do you think it will be possible in the future to train, let's say, AI to find always maybe the shortest solution, the shortest proof? Because also this is, when for humans, this is also very difficult, I guess. But I mean, can you say a bit about that? I mean, what do you think will be possible in that
Yes,
respect?
so I think it's totally. I think in order to do that, we need to be able to teach AI to evaluate, to tell us, given a proof, it is a good solution, is it a bad solution, is it an elegant solution? I think to do that, I think we might need some kind of training data, either like we need like humans to tell us, okay, this is a good proof, this is a bad proof, or maybe we need to find out some heuristics, some idea on like to identify, okay, this is a good one and this is a bad one. We might be able to do for AlphaGeometry, for example, we look at the proof length, could be one approximation in terms of like it is a good solution or not. But I think of course it's not a perfect one, because I think like for mathematics, when you solve it, you need to see everything, right? You need to understand, oh, this is all that circle. We're making use of like inverse geometry. And actually, one thing I forgot to tell is that after such a long run, after building AlphaGeometry actually haven't been able to solve the problem that my math teacher was able to solve at 1979, which is a very simple geometry problem I showed you at the beginning, where the 2 point travel with the same distance. AlphaGeometry hasn't been able to solve that because of the way that the language was constructed as well.
Okay, yeah, thank you so much. So, I mean, my second question concerns, I mean, what you also said that, so this model, I mean, is specifically for geometry, but you said that, I mean, ideas could also be used for other, let's say, areas of mathematics. So I myself come from the area of functional analysis. So I'm wondering, I mean, because there are, let's say, it is very different from geometry. Geometry is very systematic in some sense, but I mean, for, let's say, functional analysis, you have convergence, and I mean, some also continuous like objects. I mean, to which extent do you think it will be possible, and how long will it take to actually translate those ideas now to other areas of mathematics?
Yeah. So, like we picked geometry because I think, let's say in AI mode, there's 4 areas. So we have like algebra, number theory, geometry, and combinatorics. So geometry probably the easiest area that we was able to tackle because it's very concrete. We can construct every point, lines, circle, and we know the target solution. And then that makes everything so much easier for geometry. It's still a big challenge, I think, like to get to areas like what you just said, functional analysis, or like algebra, number theory, or even combinatorics is very hard as well. So I think we hope that the idea that we present, like the way that we think about like how do we generate a large amount of data, so that kind of idea can be applied. I think, like for example, for your case, I think maybe we need to come up with a set of rules. We need to like concrete, build up the kind of a language for functional like analysis or something like that. So in summary, I think there still need to be some work there. But I think like I hope that some of the idea from AlphaGeometry can be applicable, can be an inspiration for others.
Yeah, thank you. So again, maybe to the audience, I mean, please write your questions in the chat, and then I can read it here. So right at the beginning, you said that this is a way to AGI, so to artificial general intelligence. So what are your thoughts? How far are we actually from AGI? You said mathematics is a key step. But now, for instance, let's say you can extend it to all of mathematics, then, I mean, how far are we from true AGI? And will we ever reach it? I mean, there are, let's say, controversial discussions also, I think, Jan de Kuhn and so on. I mean, everybody has their own opinion. I mean, what's your take on that?
Yeah. I think well, I think this is of course, like, I think people might have different answers. I think on one side you might have thought that, okay, with the appearance of ChatGPT, like Bard, Gemini, it's failed AGI in a way that somehow now the AI can just in one go help you write email, write resume, compose a poem. It wouldn't be possible when I was a PhD student. I would actually do natural language as a focus. I would imagine building such system. You would need a lot of components, but somehow now you only have only a single large language model that can do a lot of things. So it felt AGI already at some point. But I felt like with that kind of fast development of AI, maybe in a few more years, hopefully, I don't know, could be 2030 if I can speculate, maybe. So I think we can get pretty close. And in fact, I think like maybe could be this year, next year, people maybe already be able to win. AI can also might have a chance at the IMO, could be like Go level IMO or something like that. And then hopefully 3-4 more years, maybe they can prove like an important conjecture or discover new mathematical knowledge by themselves.
Okay, that sounds exciting. So now, I mean, we also have some questions here in the chat. So the first is asked by Massimiliano Esposito. I said, ciao, and thanks for the talk. Is it possible that this tool works because geometry is decidable? Like, have you tried to use AlphaGeometry to number theory? And then he also said, how other fields of IMO can be adapted to this trick you use of adding a point and then run the neurosymbolic solver.
Oh yeah, so I think as I said, like geometry is an area on its own to extend to other areas of mathematics that need to be non-trivial amount of work. So I think they all come into the fact that we need to figure out the rabbit or the kind of like some kind of insight. I think that would be something that we can hope that we will be able to teach the machines. So I think number theory is challenging. I think we might be able to make some progress. Let's say the kind of like approach like AlphaGeometry for algebra. Algebra might be doable, but again, might need some work. But number theory or for like combinatorics, maybe we need to think about something else as well. Could be large language model because it's closer to the kind of language that we use to like the kind of arguments that we use in everyday lives.
Mm-hmm. Thank you. The next question was asked by Edgar Delgado Eckert. He asked, besides those theorem proof pairs, did you train the model with axioms such as Euclid's axioms as well?
Mm-hmm. Yeah, so AlphaGeometry based on the basic Euclidean rules. Of course, I'm guessing maybe you think about like what are we able to maybe just from a few axioms and then somehow we can discover new geometry, new math. I think if that is the question, I hope that we can do in the future where we can start up with a few basics axiom, and the AI can construct more rules and more rules, and then build larger and larger data examples to then discover the whole like Euclidean geometry.
Mm-hmm. Thank you. So the next is by Michael Speiser. He's asking, is the search by the symbolic deduction engine done in essentially brute force fashion, or can the neural network also guide the search?
Yeah, so I think right now they operate independently. So so when we introduce the new points and line, the magic construction, then we pass it into the symbolic engine, which works independently with the neural networks. It receives the fact, okay, there's new edges, there's new leaf node in the graph, and then it build up the closure. So it go through all the deduction rules and then build up the new closure. So we could have let them to give insight to one another, but I think right now for simplicity, we will just let them work independently.
Mm-hmm. Okay, so then Michael Speiser, again, thank you for the interesting talk. Have you looked at how well AlphaGeometry performs as a function of the number of elements required for a proof? E.g., how does it perform if 20 points, lines, segments need to be present in a minimal proof versus if only 10 elements are needed? And is there a maximum number of elements that the system can handle?
Can you say one more time, please?
Yes. So he said,
Gita, I've just
yes.
added it to the hosts and panelists. So Tang, you can actually read the question as well.
Okay. Yeah, maybe
Okay,
Gita,
maybe you can, yeah.
you can help read again.
Have you looked at how well AlphaGeometry performs as a function of number of elements required for a proof? So how does it perform if 20 point segments need to be present in a minimal proof versus if only 10 elements are needed? And then is there a maximum number of elements that the system can handle?
Yeah, I think that's a good question. So I think right now there's not a maximum number of elements that the system can handle, but of course, like when we have more things, then the closure can be bigger. Will take more time as well. So so if you want to fit within the IMO limit, so then we have to take that into consideration. And then it's also like but I think in theory it shouldn't be a maximum number of elements. And of course, I think like for more complex problems, like more line points and segments, I think of course it's more challenging for AlphaGeometry. I think we usually have a plot in terms of like how AlphaGeometry solve things with respect to the proof length. Also how it correlates with the human score as well. So of course, like there's more challenge for like AlphaGeometry for more complex problems, where it might need to construct like more points, more lines. So some problem it might not be able to solve.
Hey, are there any more questions from the audience? So I don't see any further questions. Then, yeah, so let's thank our speaker again. That was an amazing lecture. I think we all learned a lot and look very much forward towards, let's say, covering everything of mathematics and then also AGI in the end.
Yeah,
thank you so much.
Thank you so much. Okay. Bye.
Thank you for participating in today's AI for Good session. We hope you've learned something new, innovative, and engaging in today's event. We now encourage you to continue the conversation on the live video wall in the neural network. Here you can ask questions, like and comment, share links, complete the poll, connect with interesting profiles, or speak one-on-one using the chat and video function. We invite you to explore the lobby, try the smart matching quiz, visit the virtual exhibits, poster boards, the eShop, and build your personalized AI for Good program. Let's shape the future of AI for Good.
The AI for Good Global Summit, convened by ITU, recognizes the joint responsibility of governments, the private sector, United Nations agencies, academia, and others to ensure AI reaches its full potential while preventing and mitigating harms.
And it's a moment that calls for action. And today I'm calling on each of you to use this summit to help the world to better understand what kinds of regulations, what kinds of guardrails we need to put in place right now. So together, let's make it innovative, let's make it safe, and let's make it responsible for all. Thank you very much.
Mm-hmm.